All right, in this video, we are going to be going over section 3.5, zeros of polynomial functions. So we've already talked about the intermediate value theorem and how we can use that the theorem to help us locate where the zeros of a polynomial could be. Like we can use it to determine if there is like a zero between two values a and b. So that is still an important tool for us, but now we are going to look at a few new theorems here in this section. And so our first theorem is going to be the remainder theorem, which says that if a polynomial f of x is divided by x minus k, then the remainder is the value f of k. Okay, so the nice thing about the remainder theorem is that like if we have some polynomial that is kind of hard to evaluate at a particular x value, then instead of trying to evaluate the function by hand, what we can instead do is use synthetic division to go ahead and divide our polynomial f by x minus k when we're trying to evaluate it at x equals k. And then what we get for the remainder is going to be the function's value at x equals k. And so let's look at an example here. So given the function, the polynomial function f of x, which is equal to 2x to the 5 minus 3x to the 4 minus 9x cubed plus 8x squared plus 2, we want to use the remainder theorem to find f of 0 and f of negative 3. All right. So to evaluate f of 0, we want to divide f of x by x minus 0 or x plus or minus 0. It doesn't really matter about the sign here because we're dealing with 0. So minus 0 is the same as 0. They're both just 0. So we will write 0 for our divisor. So let's go ahead and set up the synthetic division. And I realize, so this might seem a little bit silly using synthetic division and the remainder theorem to find f of 0 for any polynomial because of course f of 0 is just going to be equal to the value of the constant term in the case of polynomials because, well, the rest of the terms, they're just going to involve a factor of the variable x, and so when we go and plug 0 in for x, well, that whole term is just going to become 0, and so all we are left with is just the constant term. So it might seem a little bit silly to use the remainder theorem here to evaluate f of 0. And really our motivation for using the remainder, well, for using synthetic division and the remainder theorem to find f of 0 is that we already know that our answer should be 2. So this is more of us kind of using an easy to calculate value of f. To kind of check and see for ourselves, you know, is this theorem any good? All right, so first we want to notice when we're setting up the coefficients for our dividend, so we want to check and see if there's any terms missing that we need to put in a 0 for. So here f of x is a degree 5 polynomial function, and if we look, we have our degree 4 term, we have our degree 3 term, our degree 2 term, and then we have our constant or degree 0 term. But notice what's missing is the degree 1 term or the linear term. So that just means its coefficient is 0. So the coefficients we'll put for our divisor in the synthetic division are going to be 2, then minus 3, then minus 9, then 8, and then a 0 for our missing linear term, and then 2. Okay. And so the first thing we're going to do is just bring down the 2. And then we want to do 0 times 2 is just going to be 0, of course. Add that to minus 3. And that's going to be minus 3. And then minus 3 times 0 is 0. Add that to minus 9 is going to be minus 9. And then minus 9 times 0 is 0. Add that to 8. And we're going to have 8. And then we will have 0 times 8 is going to be 0. Add that to 0. We're going to get 0. And then finally, we'll have 0 times 0, which is going to be 0. Add that to 2. It's going to be 2. And so this is our remainder, is 2, which is kind of what we expected to end up with. So we could say by theorem, f of 0 is equal to 2. All right. So now let's use the remainder theorem to calculate a value of our given polynomial function f of x. That would be a little bit harder to find without the remainder theorem. So we want to now find f of -3. So this means that we are going to be using a positive 3 for the divisor. And yeah, that's the thing to remember when using synthetic division is that if we are trying to divide a polynomial f of x by a binomial x minus k, then when we're setting up the synthetic division, we want to change the sign of k from minus k to, of course, just k for our divisor. And so here we would be thinking about dividing f of x by x plus 3 or x minus a minus 3, which is the same as x plus 3. And so we have a minus 3 for our divisor here. Okay. Oh, and yeah, I forgot that we had this copied, so I didn't have to write it again. All right, so now we have our synthetic division set up for dividing f of x by x plus 3. So we're going to bring down the 2 for free, and then we have 2 times minus 3 is going to be minus 6. Add that to minus 3 is going to be minus 9. And then we have minus 9 times minus 3 is going to be a positive 27. Add that to minus 9, and we are going to have a positive 18 now. And then 18 times negative 3 is going to be negative 54. Add that to 8, and we get minus 46. And then we have minus 46 times negative 3 is going to be a positive 138 plus 0 is going to be 138 is what we bring down next. And then 138 times minus 3 is going to be negative 414. All right, and then 2 plus minus 414 is going to be a minus 412. So that's our remainder. And so f of -3 is equal to minus 412. All right, and then we have our next theorem, which is going to be the factor theorem. So the factor theorem says that f of k is equal to 0 if and only if x minus k is a factor of f of x. So the factor theorem is kind of like the combination of the remainder theorem and what we said earlier with the division algorithm. And by what we said earlier, I mean in the section 3.4 notes. So what we said with the division algorithm is that if we get a remainder of 0 when we try to divide our polynomial f of x by a polynomial, in this case x minus k, since we're in the particular context of just dividing by linear binomial factors with a leading coefficient of 1. So we said with the division algorithm, if we ever have a remainder of 0, then whatever we had for our divisor is a factor of our dividend. And then what we just said about with the remainder theorem is that, well, we said if a polynomial f of x is divided by x minus k, then the remainder is the value f of k. And so if f of k is equal to 0, well, this just means that the remainder when we divide f of x by x minus k is going to also be 0. All right, and so we have an example here. And in this example, we're asked to use the factor theorem to find the zeros of the polynomial function f of x, which is equal to x cubed plus 4x squared minus 4x minus 16, given that x minus 2 is a factor of the polynomial. So since we are trying to divide a degree 3 polynomial by a degree 1 polynomial, what we should end up with for the quotient is going to be a degree 2 or a quadratic. So a degree 2 polynomial, or in other words, a quadratic function. And so once we have the quadratic for the quotient that we're going to end up with after we do this division, we can go ahead and just use the AC method of factoring to go ahead and factor the quadratic. And then once we have that quadratic factored into its two binomial factors, we will have all three factors for f of x minus 2, and whatever two factors we get from factoring the quadratic. But before we can factor that quadratic, we have to figure out what that quadratic is. So let's go ahead and do the synthetic division to find the quadratic quotient. So here, since we're trying to divide by x minus 2, we're going to use a positive 2 for the divisor in the synthetic division. And then let's check. So f of x is a degree 3 polynomial. We have our degree 2 term, our degree 1 term, and our constant term. So we are going to have no zeros for the coefficients in the dividend. So I'll have 1, 4, minus 4, and then minus 16. And then we're going to bring down that leading coefficient 1. It's going to be the first term for our quotient, or it's going to be the coefficient for the first term of our quotient. Then we multiply that by 2. So multiplying 1 by 2 gives us 2. Add that to 4 is going to be 6. Multiply 6 by 2 is going to be 12. Add that to minus 4 is going to be a positive 8. And then multiply 8 by 2 is going to be 16. Add that to negative 16, and we're going to get 0 for the remainder. So we have f of k, or rather f of 2 is equal to 0. Which confirms to us, according to the factor theorem, what we were told in the statement of the problem, that x minus 2 is a factor of f of x. All right, and then now we want to write the quadratic. So this is going to be our degree 1 term, so 8, and then this is, our degree 0 term, our constant term, so just a 8, and then this is going to be our degree 1 term, so 6x, and this is going to be the coefficient for our degree 2 term, so x squared. So when we divide f of x by x minus 2, what we end up with for the quotient, again the remainder is 0, is going to be x squared plus 6x plus 8. And so we can factor using the AC method. So we have a is equal to 1, b is equal to 6, and c is equal to 8. So a times c is equal to 8. And since that leading coefficient a is equal to 1, we can use the shortcut version of the AC method. So once we figure out our two numbers for the AC method, we can go straight to writing our binomial factors using those two numbers. So for 8, well, let's look at the different ways we can factor 8. we could do 1 times 8 or 2 times 4. Since we're trying to add to a positive, we're not going to consider the factorizations where both factors are negative. So this would be all the factorizations we could consider. And if we look at 2 times 4, well, 2 plus 4 is equal to 6. So this is going to be the factorization that we take, because it adds up to b. And so we can go and write, okay, x squared plus 6x plus 8 is going to be equal to x plus 2 times x plus 4. All right, and so these are going to be the other two factors for f of x. So all told, we can write f of x now in factored form. It's going to be equal to x minus 2 times x plus 2 times x plus 4. And if we wanted to be extra sure here, so just for the sake of time, I'm not going to have us go through this, but if we wanted to like get some extra repetitions using the factor theorem, what we could do is we could take each of these other two factors, x plus 2 and x plus 4, and go and divide f of x by either of these factors using synthetic division. And what we should find in each case is that the remainder is going to be 0.